It's afternoon here, Dr.
Yes.
Dobrautz. Good to see you, Dr. Dobrautz. I'm Yanuar, your moderator for your presentation today. You may call me Yan. How may I call you?
Werner. So Werner, my
Werner.
first
Okay.
name, so that's
Yeah.
fine. Yes,
Yeah,
thank you.
that's easier for me too.
Yes.
Okay. Nah. Uh, we will start the official introduction soon. Uh, Werner, can you please test your screen sharing feature?
Yes.
Okay.
Share. This should be just the presentation then, or?
Sure. Looks good.
Okay, cool.
Looks good. Okay. Okay. Let's start our colloquium today. Thanks for everyone joining us, and welcome to BRIN Quantum Physics Colloquium. I am Yanuar, the moderator for today and a researcher here. For your information, we organize the colloquium twice a month. We invite both internal and external speakers. Today, we are honored to have Dr. Dobrautz, Werner, as our guest speaker. Let me introduce our speaker, Dr. Dobrautz. Werner obtained his PhD in computational quantum chemistry at the Max Planck Institute for Solid-State Research and the University of Stuttgart. He was a Marie Sklodowska-Curie postdoctoral fellow at Chalmers University of Technology in Gothenburg, Sweden. He now serves as a Dresden-concept research group leader, jointly appointed at the Sketch.ai in Dresden and Cases in Görlitz. He leads the AI for Quantum Research Group that focuses on developing an approach based on high-performance computing and quantum computing. And this is important for students. His group, I read from your website, his group has PhD and postdoc opening, Werner. And his talk today is titled Reducing the Quantum Circuit Footprint for Noise-Resilient Quantum Chemistry using the Transcorrelated Method and Adaptive Circuit Ansatz. Werner, you have 1 hour for your presentation, followed by 30 minutes for Q&A session. And to participants, if you have any questions during the presentation, you may post your questions in the chat. And Werner, if you find any question in Zoom chat, just ignore it. You may ignore it because I will read the questions later after you finish your presentation. Okay, time is now yours.
Thanks a lot for the introduction, and thanks a lot for having me. Yeah, so as introduced, my name is Werner Dobrautz. I'm a research group leader now here in Dresden since December of last year. Sorry. And yeah, the topic of my talk is how can we essentially reduce the circuit footprint to enable more noise-resilient quantum chemistry calculations on current quantum devices. And the main two methods I wanted to talk about today are the so-called transcorrelated method and its combination with so-called adaptive quantum circuits. And a short outline of my talk, I will start with the background and the motivation of the research me and my group are doing. Then I will introduce this main method of transcorrelation that enables to reduce the computational footprint on current quantum hardware. And then I will present some results both for ab initio quantum chemistry problems, but also for lattice problems like the Hubbard model relevant to solid-state physics. And then I'll dig into adaptive circuits Ansätze before I conclude. Yeah, so on the background and motivation. So I always like to start highlighting one of the most important industrial processes of our time, which is the Haber-Bosch process, where nitrogen and hydrogen are under extreme pressure and temperature transformed to ammonia, which is a crucial process for fertilizer production. But since this strong triple bond of nitrogen has to be broken during this process alone is responsible for up to 2% of the current world energy consumption. At the same time, though, there is a biological pendant of this process where bacteria living close to the roots of plants can do this process under ambient pressure and temperature. It is, however, not yet fully understood how this process is catalyzed, and understanding this process might allow the design of biocatalysts for a more efficient and greener ammonia production. Although we cannot fully understand the process, we can at least identify the relevant molecular systems that act as catalysts for this process, which in the case of this nitrogen fixation problem, it's called, is the so-called FeMoco cluster in the nitrogenase protein of these bacteria. And these so-called transition metal clusters act as catalysts. However, although we can identify these clusters, an experimental study of these compounds is also very complicated, as they are embedded in this very complicated biological environment. Which is why we need the aid of numerical studies to understand the relevant quantum phenomena of these processes to very high accuracy. And the good thing about ab initio quantum chemistry and electronic structure theory is that we do have the equations at hand that we need to solve. It's essentially just solving the Schrödinger equation to get information, all the necessary information about these systems. But since we need to understand these processes to very, very high accuracy, solving these equations scales exponentially with the system size on classical hardware. Which is why the aim of my group's research is to figure out how can we combine both a high-performance computing approach combined with quantum computing to potentially enable a computational speed up for these so-called strongly correlated problems to allow the study of relevant, larger, more relevant system sizes. And what is at the heart? So what do we need to solve in a little bit more detail? It's, as mentioned, the so-called the Schrödinger equation that allows us then to get insight into the chemical and physical properties of these systems. And it can be both like in the static and time-dependent form of the Schrödinger equation. And all the necessary information of a physical and chemical system are contained in the so-called electronic molecular Hamiltonian, H, where also H actually does not look too complicated. It essentially only contains a kinetic energy term for all the electrons of a system, and then an attractive potential term between the electrons and the nuclei, as well as the electron-electron repulsion term, the Coulomb repulsion. And the problem now is that this Coulomb repulsion term correlates all the electrons of a system, and this two-body interaction makes the analytic solution of the Schrödinger equation too complex for any problem beyond the hydrogen atom. Which is why we do need the aid of numerics and approximations to solve this equation to high enough accuracy. And depending on how accurately we want to solve this problem, there exists like a long existing hierarchy of methods and theories to solve the Schrödinger equation. And if we plot this like in a diagram where we plot accuracy and cost versus the system size we can study, at the bottom, of course, we have so-called mean field methods, where the interaction of one electron is taken into account with all the other electrons in a so-called mean field approximation. And these are methods like Hartree-Fock and density functional theory, which are very, very efficient and can be applied to very, very large system sizes up to thousands of atoms. But the more explicitly you take this electron correlation into account, the more accurate your method becomes, but also the more costly it becomes. And at the top are like very accurate methods like quantum Monte Carlo, density matrix renormalization group, and so on. And at the top is the so-called exact solution of a problem in a given basis set, and this scales exponentially with the system size. So these very accurate methods can only be applied to very, very tiny problems, too small to understand relevant phenomena of these interesting compounds. And the hope is that quantum computing, especially for this quantum mechanical problems, might be able to provide this computational speed up to extend the reach of these very highly accurate methods. And why does this exact solution scale exponentially? So I wanted to dig into a little bit. So the exact solution is also in chemistry speak called so-called full configuration interaction, or FCI. And the idea there is that we really want to write down the eigenfunction of our Schrödinger equation as a linear combination of all possible so-called Slater determinants of a system. And if we formulate our problem like in so-called atomic or molecular orbitals, we have essentially various energy levels that can be occupied by electrons with an up or a down spin. And for the FCI solution, we actually need to consider all possible distributions of electrons in these available molecular orbitals. And this then, of course, scales exponentially with the system size. So already at very, very small problems like F2, where one has 18 electrons only in a minimal basis set containing of 18 orbitals, we are already at the system sizes that classical conventional hardware can struggle with. Which is why, of course, this demonstrates why we need efficient approximations to target this exact solution. And in addition, in electronic structure theory, quantum chemistry, there is one additional problem to this scaling behavior, which is the so-called cusp condition. And this is a mathematical condition with its origin in that if one looks at the electronic Hamiltonian, and if one thinks of what happens if two electrons actually come very close to each other, then of course the Coulomb potential term diverges due to this 1 over Rij term. And to still have finite solutions to the Schrödinger equation, what actually happens is that this diverging Coulomb potential is counterbalanced by an equally divergent kinetic energy term due to the electronic wave function having this very sharp cusp-like feature if two electrons come close to each other. And the problem now is that, so this is like a mathematical feature of the exact electronic wave function. The problem then is that these molecular orbitals we use to represent our Schrödinger equation on computer hardware, they are actually designed to be very smooth functions due to other numerical efficiency reasons. And these smooth so-called Gaussian type orbitals, they have a very hard time now accurately describing this sharp cusp-like feature of the exact electronic wave function, which means that we need to use more and more of these orbitals to accurately describe this very sharp feature. And what this then causes is that in addition to the system size scaling of our methods, we introduce another axis of complexity, so to say, that we have now like a bad scaling with system size of our methods, and we also have to use this increasing number of orbitals or increasing basis set size. And the accurate methods scale bad with both of those increasing sizes. And this also has a direct consequence also for representing our electronic structure problems on quantum hardware, because the more of these orbitals we use, the more qubits we need to use to represent our problem on quantum hardware. And having talked about quantum hardware, I actually also wanted to make the point of why do we actually believe or think that quantum computing can provide a benefit for this ab initio quantum chemistry and electronic structure problems. And this is, of course, because if we look at this exponentially scaling number of Slater determinants or basis functions, this exponentially scaling Hilbert space we have that to represent our problem in, this of course very naturally translates to a representation on quantum hardware. That if we, for example, use our qubits to represent the occupation of these different energy levels, we can actually represent this 2 to the n number of states with a linear number of n qubits by using various fermion to qubit mappings. So we need to map our problem, both the Hamiltonian and the basis function, onto the quantum hardware. And then, of course, the challenge is that we need to find and design useful quantum algorithms to actually solve our problem, to get like ground and excited state energies and properties, and maybe also dynamic properties of our system. And the most famous example for this kind of approach in near-term approaches is, of course, the variational quantum eigensolver, where the idea is that one uses like a quantum hardware and a classical computer in a hybrid form and in an iterative way, where the hope would be that we can variationally minimize our energy estimate as a function of this iterative number of iterations. But you are also, of course, aware that this approach struggles, of course, with the limits of current quantum hardware, because we do not have logical qubits. We have like noisy qubits that can introduce essentially a lot of errors and noise during our simulations. So instead of getting this perfect energy convergence, what we actually get if we don't do anything to counterbalance that, we actually essentially get random results of current quantum hardware. Which is why this is the focus of my talk essentially, is how can we limit the effect of noise to still get relevant numbers out of current hardware. And two approaches to do that is one, like if we can, of course, reduce the so-called circuit surface, like if we can reduce the number of qubits we need to use to represent our problem, as well as if we can reduce the circuit depth to prepare our estimates for our ground state wave function, and combine that then with efficient error mitigation schemes, we hopefully can get relevant numbers out of current quantum hardware. And this is essentially the focus of or one of the foci of my research group, that we want to tackle these problems of current and near-term quantum devices. Like we devise methods to reduce this number of qubits essentially and the circuit depth, but we also work on developing various quantum circuit Ansätze, as well as algorithms to solve the Schrödinger equation to high accuracy. And we also focus on how can we mitigate noise, as well as, which is often a bit overlooked, but also this classical optimization step can also be challenging if one uses these hybrid quantum classical devices, where we use the quantum processing unit together with a CPU to, for example, iteratively update the parameters of a parameterized quantum circuit. So let's focus first on this method of transcorrelation that enables to reduce the necessary computational footprint on quantum hardware by reducing both the number of qubits we need, as well as the circuit depth we need to apply to get accurate ground state wave function approximations. And the idea of this transcorrelated method is that since we know this very sharp feature of this, or this cusp of the exact electronic wave function that induces this need for using a large number of orbitals, that induces the need for using a large number of qubits, why don't we make use of the fact that we know how this exact electronic wave function looks, at least for small electronic distances. And the idea then is of this so-called explicitly correlated methods is that we make an ansatz for our wave function psi, where we use a function f that incorporates this very sharp cusp-like feature. And there are efficient ways to design these functions and also optimize them classically with only a cubic scaling cost in the number of electrons, multiplied by now a different wave function phi that is much smoother and thus hopefully is much easier to represent with a small number of orbitals, which means we need much less qubits to represent this phi wave function. So the hope is that we will get much better energy estimates with this transcorrelated approach, or TC, with a small number of qubits compared to an approach that doesn't use this explicit correlation approach. And there are like this explicitly correlated methods. They have like a very long history, starting with the work of Kutzelnick in 1985, where people have thought about different ways to incorporate this very sharp feature, which essentially at very small electronic distances is a linear behavior of this wave function with the electronic distance. There was, for example, this initial method called R12 by Kutzelnick, which then was extended to the more general, where this R12 really just implemented this linear behavior by plugging in the distance between two electrons in this ansatz. This was then extended to a more general version by Tenno in the so-called F12 method, where we don't explicitly use just the electronic distance, but some function of the electronic distance multiplied by this phi wave function. And here is the explicit form. And the most general ansatz, I would say, is a so-called Jastrow ansatz, where one makes this specific form of the ansatz for our wave function with this exponential form, where this function j is a function of some optimizable parameters jij times polynomial functions of the electronic distances. And these Jastrow type Ansätze, they have a long history in especially the variational Monte Carlo community. And they have been used for decades, essentially. And there are efficient ways to optimize this so-called Jastrow factors on classical hardware with variational Monte Carlo, with this mentioned cubic scaling cost with the number of electrons. And usually, like what variational Monte Carlo does is, one makes an ansatz for the wave function and just optimizes this Jastrow factor, and then you have a variational estimate for your ground state energy. What we instead do in this transcorrelated method is that we use this Jastrow ansatz, e to the power of j, as the starting point. So we use the similar approach, like we use VMC to optimize this Jastrow factor. To capture this cusp condition, as well as also part of the electron correlation already. But then, having this optimized Jastrow factor, we actually incorporate this factor into the Hamiltonian by solving a similarity transformed problem. And if we go step by step, like what the ingredients are, that is, we start with this with the Schrödinger equation in its original form, and then if you plug in your ansatz for your Jastrow ansatz for your wave function, one actually ends up at this transform problem. And if one then multiplies this equation from the left with e to the minus j, we end up with this line at the bottom, where on the left we have this similarity transformed problem. So an operation e to the minus j, h e j is a so-called similarity transformation, times now this smoother wave function phi. And here on the right, since E is only a number, this e to the minus j commutes through. So you actually end up with a eigenfunction or eigenvalue equation again with the same energy, but a different operator and now a different wave function phi, which is now this smoother wave function, where the hope was that this phi is easier to represent with less basis function, and thus we have this immense resource reduction on quantum hardware. And of course, one might wonder, like, okay, we have this similarity transformation, but how do we actually compute this transform problem? And the good thing actually for general Jastrow type Ansätze and the molecular Hamiltonian, actually, if one performs the Baker-Campbell-Hausdorff expansion to solve this similarity transformation, one actually finds that all the terms above the second order, so actually you would have an infinite sum of these nested commutators, but actually due to the specific form of the molecular Hamiltonian, all the terms above second order are zero, since only the kinetic energy operators in H do not commute with this Jastrow factor J. So one can actually perform an exact transformation of the Hamiltonian with this Jastrow wave function. The consequence though, I mean, these are details, so it's not so important to go too much into depth, but one then obtains the similarity transformed Hamiltonian. And what you get actually is, since it's a similarity transformation, not a unitary transformation, you actually introduce a modified two-body term, which is non-Hermitian, and you get an additional three-body term compared to only the one and two-body term in the original molecular Hamiltonian. So these are the drawbacks, but the benefit is that you have this rapid basis set convergence, that you get much better energies with much smaller number of orbitals because you target now this smooth eigenfunction phi. And since we talk about quantum computing approaches, of course, having now this free body term, and I mean, this is the Hamiltonian in first quantization. If you then write it down in second quantized form, one then of course gets your very common one and two body terms with like now a non-Hermitian two body operator. And then you have this additional free body term, which is of course like for quantum computing approaches with the measurement problem very scary. But I will show that, I mean, essentially by doing this transformation, you get essentially an order of magnitude reduction in the necessary number of qubits. So actually the formal scaling, if you look at just n to the 4 scaling of the original problem, compare it with an order of magnitude less required qubits to the power of 6, like that the crossover still is above 100 qubits. So like you have a good scaling even for very large systems. And actually there are efficient approximations to this free body term that again can reduce the scaling to just the known quartic scaling with the number of orbitals used. So which is the approximation we will use from now on. So you have a very good approximation to the free body term. So the free body term is actually not a problem in this transformed problem. But of course, since this transcorrelated Hamiltonian, this transformed Hamiltonian is non-Hermitian, variational algorithms like the VQE are of course not applicable because variational algorithms only apply to Hermitian operators. But there are various other quantum computing algorithms, specifically the so-called quantum imaginary time evolution, that is able to target also the ground states of non-Hermitian operators. And what is imaginary time evolution? The idea of imaginary time evolution is that if one looks at the time-dependent Schrödinger equation, in imaginary time evolution, one actually rotates this real-time evolution of the Schrödinger equation to so-called imaginary time by substituting to this new variable tau that equals it. And then one ends up at an equation, imaginary time Schrödinger equation, that can be formally solved by taking the limit of imaginary time to infinity and having this operator e to the minus h tau applied to some initial wave function. And the benefit of that formulation is, of course, that now, I mean, if you look at this so-called projection operator, this, if you apply it to some initial wave function, will suppress all energies higher than the ground state exponentially, because you have one ground state solution with the lowest energy, and all the energies above the ground state, if you normalize accordingly, can be essentially suppressed by this e to the minus, this negative exponential. So if you look at the coefficients during your time evolution, actually you will have the coefficient of the ground state, C0, will actually converge to 1 in the long imaginary time limit, and the coefficients of all like higher levels or higher excited states, C1, C2, and so on, will exponentially diminish to 0. And so you will also have this convergence of the energy with imaginary time to the ground state energy. And the good thing about imaginary time evolution is that it's not relying on the variational principle. It actually solves for the right eigenvector of a problem, which can also be a non-Hermitian operator, by iteratively applying this projection operator e to the minus h tau. And I mean, still one caveat, of course, is like this projection operator e to the minus h tau is again, of course, not a unitary operator. So then one could think of, okay, how should we apply this non-unitary operator on quantum hardware, which only can do unitary operations in general? And the good thing, though, is that there are various approaches, and one approach is that one can map this imaginary time evolution of your ground state to the time evolution of parameters of a variational Ansätze-based or a variational quantum circuit, a parametrized quantum circuit. So the idea is that we will, of course, on quantum hardware, approximate our wave function psi of tau with a quantum circuit as a function of some parameters. So you make this approximation, which is, of course, a unitary applied to it. And I mean, this quantum circuit can be like very general quantum circuits or these hardware efficient quantum circuits. And the good thing is that one can map the imaginary time evolution to the time evolution of these parameters of the Ansatz. And I will also skip a bit over the details because they are not too important, but one can think of this visual representation where this like two-dimensional manifold represents this unitary parameterized quantum circuits, the states this quantum circuit can represent. And you have like some initial state phi of these parameters. And what we then do is that we would have essentially this exact imaginary time evolution given here in blue, which would bring our initial state from here to this state with the exact imaginary time evolution outside of this Ansatz space that the parameterized quantum circuit can span. Since you have this unitary operation. And what variational quantum imaginary time evolution then does is that one minimizes the distance between like this exact imaginary time evolution to the variations of the parameters of a quantum circuit that lies still on this manifold the quantum circuit Ansatz can span. And this distance can be minimized with various metrics. And what we used is the so-called McLachlan's variational principle that minimizes the distance between these two states. And that then allows to map this imaginary time evolution to the evolution of our parameters. So one gets an equation for the time derivative of your parameters as some linear system of equations, where the two ingredients are like one is the gradient of the energy, C. So this is quite common. I mean, this is essentially, if we would just have minus C as the update, we would have gradient descent, but also times the inverse of a matrix, which is the so-called metric of our quantum circuit. So this is also sometimes called the Fisher information matrix, or part of the quantum geometric tensor. And this then includes information of this of the geometry of your quantum circuit metric, or the quantum circuit geometry, how this space looks. Because of course, maybe I'll also have it here. Yeah. So this quantum imaginary time evolution is also connected to the so-called quantum natural gradient method, where the idea is to incorporate the geometry of your ansatz via this metric tensor term. And the idea is that if one would have just gradient descent, that could of course be like a could have very much problems in the minimization. But by taking into account the geometry of your parameterized quantum circuit landscape, one can then actually define this natural gradient update, which is equivalent to the variational quantum imaginary time evolution, that actually is the optimal gradient direction in this curved manifold of the parameterized quantum circuit. And there are some arguments that this approach can avoid certain problems like local minima and this famous barren plateau problem of other optimization schemes. And the good thing is, this variational quantum imaginary time evolution can also be performed in a NISQ-friendly hybrid approach, where similar to VQE, like we use our parameterized quantum circuit to prepare our ground state wave function. And then on quantum hardware, we measure now, instead of the energy, we measure this metric term and the gradient term on quantum hardware. And then on the classical computer, we solve this equation, this linear system of equations, to get the updated parameters theta at the next time step k+1 and feed it back to our parameterized quantum circuit. And then hopefully we also get this energy convergence with imaginary time, also now for non-Hermitian problems. Yeah, and the benefits of this VarQITE is that essentially you don't need any optimizer for the classical system because you solved this system of equations. So this gives you the perfect update rule, so to say. And usually it's also more like robust against noise in the convergence. And as mentioned, it's applicable to non-Hermitian problems, which can be, for example, open problems or transport problems, and also this transcorrelated Hamiltonians. The drawback is, of course, that since one needs to measure also this metric term, this is a so-called second order method. And now by measuring this metric term, one introduces this quadratic scaling with the number of parameters of your quantum circuits. And this matrix A can be singular. So the inversion of this matrix can cause problems in the optimization. And to essentially target these two problems, we have at Chalmers, with some colleagues, we have developed an approximation to this quantum imaginary time evolution or quantum natural gradient, which we termed QBANG, where we combined a quasi-Newton approximation as well as an adaptive momentum approach similar to the Adam optimizer in conjunction with this quantum natural gradient. And the idea was there that we made an approximation of this metric term. We initialized it to some initial metric, but then we essentially updated our metric only in this quasi-Newton approximation approach with informations on the energy gradient. And I will not go into details of this approach, but the benefit of this approach is then that, of course, this is now only linear scaling with the number of parameters, and one can also use, for this very specific approximation, one can use the so-called Sherman-Morrison formula to directly update the inverse. So we don't have to invert the matrix, but we update the inverse directly, so you don't have the problem of singularities creeping in during your calculations. And this then caused immense reduction in the circuit evaluations and improved the convergence. For example, this is energy estimate for a water molecule as a function of circuit evaluations, and our method QBang here outperformed all or various other state-of-the-art optimizers. One small note then, so this metric term is then solved, so to say. VarQITE works for these non-Hermitian Hamiltonians in principle, but I have to give a small caveat, of course, because I mean, actually measuring gradients on quantum hardware for non-Hermitian operators, one needs to think how to do that. Because in the Hermitian gradient case, for Hermitian operators, one can just use methods like linear combination of unitaries to measure the gradients directly. But for non-Hermitian operators, this is of course a bit different. And there was a work by McArdle and TU that introduced this gradient measurement for non-Hermitian operators. What they introduced is they, like compared to the normal linear combination of unitaries, they introduced this controlled operations on the Pauli strings of your Hamiltonian in terms of sum of Pauli operators. And this, of course, introduces like a lot of overhead because these controlled Pauli terms, they can have a very bad scaling for the gradient measurements. And instead, in our work, we devised this we split up essentially the measurement of the non-Hermitian operator by splitting it in a Hermitian and an anti-Hermitian part. So you can always, having like a non-Hermitian operator, you can write down a Hermitian combination like this, H plus H dagger, and the anti-Hermitian, which is H minus H dagger. And then we separately measured the gradients of both this Hermitian and anti-Hermitian part, which is possible. And you can actually do it much cheaper compared to this controlled unitaries, and very similar to just the normal linear combination of unitary approach, but just some changes to this ancilla register up there. Yeah, finally, after all this introduction, let's come to some results. And the first system we actually looked at was the Hubbard model. Okay, now just to recap, like the main idea of this whole workflow is that we want to reduce these very large circuits by this similarity transformation that incorporates information on your wave function in the Hamiltonian to reduce it to a smaller quantum circuit that needs fewer qubits and fewer gates. And we did that, for example, for the Hubbard model first, where we used a slightly different Jastrow factor. And maybe just as a recap, the Hubbard model is like a lattice model that, for example, is used to describe magnetism and potentially also unconventional high temperature superconductivity. And in the Hubbard model, like you have discrete lattice sites that can be occupied by either an up or a down electron, and you can have nearest neighbor hopping terms where electrons can hop to nearest neighbors, and you have an on-site Coulomb repulsion term where if two electrons are on the same side, you have an energy penalty U. And for this Hubbard model, there exists also this type of Jastrow Ansätze, and most famously the Gutzwiller Ansatz. It has been studied already like in the 70s and earlier, where the idea is that we use essentially the same exponential ansatz for a wave function, but in this case we use this on-site Coulomb repulsion term with a parameter J now that essentially penalizes this on-site Coulomb repulsion, this double occupancies. And the good thing also, like for the Hubbard model, one can do also the similarity transformation of the Hamiltonian. You can actually resum this Baker-Campbell-Hausdorff then to infinite order. And the benefit for the Hubbard model, or the main benefit for the Hubbard model, is displayed in this figure, which I'll try to describe quickly. So this figure shows the coefficients, the magnitude of the coefficients of the ground state wave function for a 6-side Hubbard model at u over t equals 4 as a function of this optimizable parameter j in this Gutzwiller Ansatz. So at j equals 0, you will have the initial, like the original Hubbard model. And in blue is the coefficient of the most dominant state in this ground state wave function. So the Hartree-Fock state, if you think of it in quantum chemistry speak. And in orange are the sum of all the other coefficients in the wave function. And what you can see is, as a function of this j, actually, this most important state can actually be made more important. So you have like a more compact wave function, which is dominated essentially by one state alone, and also only a tiny fraction of the remaining states. Because with this ansatz, you essentially fold correlations into your Hamiltonian, and you make your then eigenfunction much easier. And the question we investigated then was, does this increase compactness of the right eigenvector? I always talk about right eigenvector because non-Hermitian operators actually have a different right and left eigenvector. So that's an important caveat. The question was, does this increased compactness mean that we need less quantum resources, essentially shallower quantum circuits, to represent this easier wave function? And of course, I wouldn't tell you about it if not, but yes, the answer was yes. You need less resources essentially to target this transcorrelated wave function phi. For example, here on the right are the absolute energy errors for a 4 and a 6-side Hubbard model as a function of layers in a unitary coupled cluster ansatz. So in blue are the original Hubbard model results, where if you use only one layer of a unitary coupled cluster, you still have quite some energy error for the 4-side Hubbard model. But if you target this transcorrelated wave function, which is much more compact and simple, you get away with only one layer essentially, with orders of magnitudes increased accuracy. And this is also the case for the 6-side Hubbard model, for example, where only with one layer we have very accurate results already, while you would need much deeper circuits for this original Hubbard model problem. So you compress the circuit depth in this Hubbard model case. We did also calculations when this was quite a long time ago now. So it was very small quantum circuits with only 5 qubit devices. But we also did then studies on the 2-side Hubbard model using this transcorrelated approach, where also on real hardware we found like better results in this teal and light pink curves are the results for this transcorrelated problem on real hardware, on noisy simulations that are much better than the original Hubbard model. But I think I have to speed up a little bit. So let me also go to then the ab initio quantum chemistry problem cases. And there the benefit is twofold. Like for the Hubbard model, caveat, since you have like a complete basis in the Hubbard model, you don't have this reduction in the number of qubits. So you only have this compression in the circuit depth. While for ab initio quantum chemistry problems, the main benefit is that you need less qubits, less orbitals or spin orbitals to get accurate energy estimates. And this, for example, is shown here for a small test case, the beryllium atom, where this is the total energy of the beryllium atom as a function of this basis set size, the number of qubits you need to target the system, where blue and orange are conventional approaches without this transcorrelated approach. And there you can see, to get to like the estimate of the so-called complete basis set limit, which would be the limit of an infinite number of qubits or spin orbitals, you need like almost 200 to get to get close to this conventional or the CBS estimate. While the star results here are this transcorrelated approach, and there you can see you have this order of magnitude reduction in the number of qubits you need to use. Like with around 25 qubits, you are essentially within chemical accuracy. This is now real chemical accuracy to the CBS estimate to this result. Similarly, we also use that then to study not only atoms, but small molecules like lithium hydride, where we showed both like the bond dissociation curve, like the energy as a function of the distance between lithium and hydride atoms, where this transcorrelated approach essentially gave very good results close to the CBS limit with a very small number of qubits. And maybe more prominently it's shown here on the right, where this is the dissociation energy of lithium hydride, which means the energy difference of a dissociated lithium and hydride and this bound lithium hydride here, molecule here at the equilibrium bond distance. And this is now compared to experimental results. So the dashed line is experimental dissociation energy. And again, in green, for example, are these no transcorrelation, like original results, where you need like, let's say, 100 qubits to get accurate estimates for the dissociation energy. While if you do this transcorrelation here in blue, you already have like a very strong reduction in the number of qubits you need to use. And if you then combine that with some pre-orbital optimization, which I mean, we can talk about it later, but here, instead of using so-called Hartree-Fock orbitals, I used natural orbitals based on perturbation theory second order. You essentially get away with less than 10 qubits to get accurate numbers of this dissociation energy with quantum imaginary time evolution. But a big caveat, of course, the orange results are in simulation. So they are using like noiseless quantum hardware in simulation. While if you then do this actual calculation without any error mitigation approaches, you get, unfortunately, the result down here. Like this is a noisy simulation, and then you get estimates very, very far off, actually with a different sign actually than the correct dissociation energy. So this then shows you like compressing the circuits alone is not enough. You also need to combine it with error mitigation schemes. And one error mitigation scheme we have developed at Chalmers is the so-called reference state error mitigation, where the idea is that if you have like a good reference state that you can easily calculate classically, but also prepare on quantum hardware, why not use this reference state to estimate like the effect of noise of your quantum circuit? And this, for example, we did for quantum chemistry problems. That's quite natural then to use the Hartree-Fock state as your reference state. So what we did then, like we measured or calculated the Hartree-Fock energy here in at 1, which you can do efficiently classical, of course. And we also prepared the Hartree-Fock state, including all the other circuit elements that we will then use in the VarQITE or VQE minimization. We prepared that on quantum hardware. And then essentially you can measure what is the effect of noise on your Hartree-Fock estimate. And then like saving this delta in energy and then doing a VQE optimization on your quantum circuit, we then use this initial like displacement or this initial error difference, energy difference to mitigate the final VQE results. And the hope then is like if your solution, your exact solution is not too far from the Hartree-Fock in parameter space, that you can get a good approximation error mitigation also on quantum hardware. And for example, we did that very back in the day with the 3-qubit device at Chalmers University in Gothenburg, where like in blue, you would have like your regular VQE results. And if you then do this reference state error mitigation, you essentially get results on top of the exact results for this hydrogen dimer. If you look closely, you will see, of course, like at this equilibrium distance, like hydrogen, there the exact result is quite close to the Hartree-Fock initial state. But in this stretched hydrogen regime, Hartree-Fock actually is not a good approximation. And then you can also see that the effect of this error mitigation becomes worse, which is why recently we also extended this reference state error mitigation to multi-reference state error mitigation, where the idea is we don't use just the Hartree-Fock state or a single state to determinant state, but we actually prepare a multi-reference state on quantum hardware based on some classical heuristics to then use this state as the error mitigation for this more strongly correlated multi-reference problems. Having all said this, if we now combine this error mitigation scheme with this reduced circuit surface due to the transcorrelated approach, then we actually get results very close to the experimental results on quantum hardware, where initially, if one would have needed 100 qubits without doing any sophisticated approaches, we reduced the necessary resources to even 4 qubits only to get accurate estimates for this dissociation energy of lithium hydride combined with these error mitigation schemes on real hardware. So this is then really performed on real hardware. It does have some quite big error bars, but at least one is in the right ballpark for these experimental reference numbers. Maybe I'll skip over this, but then one can also extend this to not only calculate pure energy differences or total energies, but we also then were able to calculate some spectroscopic constants of H2 and lithium hydride to some quite high accuracy with a very, very small number of qubits. But looking at the time, I will also then go into this approach on adaptive circuits. So for now, essentially, we have used, we have a picture, like we have used fixed circuits for our problems. For example, this hardware efficient RY ansatz, like it's a fixed pre-given circuit that we use to estimate our ground state wave function. The idea of adaptive circuits is that instead of a fixed circuit to represent our ground state, we iteratively, adaptively grow like the circuit during our energy minimization. And this was initially introduced by Grimsley et al., where the idea is that having some operator pool based on some theory, usually unitary coupled cluster or some qubitized form of unitary coupled cluster, we essentially measure gradients of our energy with respect of all these operators, and then at each iteration add the one operator that, or like there are various novel approaches, but essentially add one operator that minimizes the energy the most. And this is then done iteratively. Essentially, you add one operator, you measure the energy, you optimize the parameters, and you do that until you converge your result with the added operators. And our conjunction then was, can we combine this transcorrelated approach with this adaptive circuit Ansätze, where the idea is that like initially we had our very big circuit in red. We used this transcorrelated approach to reduce the number of qubits and the circuit depth. And then can we combine it with adaptive circuits to initially reduce the circuit depth even more, with the hope that by doing the similarity transformation, can we essentially reduce the important pool of operators of our original problem to a much smaller subset in our similarity transformed problem? And the good thing is that doing adaptive optimization, which is initially was introduced for VQE only, can be combined with variational quantum imaginary time evolution. That was introduced by Gomez et al. In 2021, where the idea again is, instead of doing these derivatives with respect to the energy of your operator pool, you actually add those operators to your ansatz that minimize this distance in imaginary time evolution the best. So you don't use the gradient as the measure to add operators adaptively, but you use this distance of the exact imaginary time evolution to the variation in parameter space of your circuit ansatz and add those operators that minimize this distance at each iteration the best. And this we then combined essentially with transcorrelation. So my student Erika Magnusson did that. And then we combined essentially transcorrelation with this adaptive variational quantum imaginary time evolution. And here we then studied 3 different problems like H4 in a square geometry, lithium hydride, and the water molecule. And on the top are the total energy versus the bond distances of these molecules. And maybe if we focus on lithium hydride, where the effect was the largest, like in red are the results of just an adaptive calculation without transcorrelation in a so-called minimal basis set, STO6G. And here the results are in red for 3 points. And the reference results are both like the exact solution in a quite large basis set here in black that is calculated classically, as well as some estimates for the complete basis set limit, which are the triangles, the blue triangles. So the blue triangles are the ground truth. And if you do like adaptive kite without transcorrelation, you get the red results. So you're quite far from this ground truth. But if you then do transcorrelation on top, you get this green results. So you get this, the main benefit of transcorrelation is this much better energies in the same basis set. So this uses the same number of orbitals as these red numbers, the same number of qubits. And then additionally, here on the bottom are the number of operators that are adaptively added during the adapt kite optimization. And in red are again like the number of operators that are added for the red results up here. And just to say, the full number of operators for this unitary coupled cluster ansatz would be 640 operators or gates essentially. So you already have like doing this adaptive adding, you have like a big reduction already, like to around 100 for this red case compared to the full operator pool. But in addition, like if you do this transcorrelated approach, like you get better energies, but you also need less operators. So due to this wave function being essentially more compact, easier to represent, you also get a benefit in the circuit depth. Like you have like, you get much better energies with having to spend less effort. And even more so, sometimes having this more compact right eigenvector can cause better convergence of the calculations compared to the non-transcorrelated results. For example, there were 2 cases, like for H4 in a square geometry with a distance of 1 angstrom. Actually, in red, the original calculation without transcorrelation should converge to this dashed line here, but actually it fails to converge, even using, it fails to converge due to some optimization problems. While if you do transcorrelation, like you have the better energy, lower energy to begin with, but also you actually manage to converge to this result compared to the non-transcorrelated problem setting. So this happened for H4 as well as water, where also like the red curve got stuck in a local minimum. Both transcorrelated approaches. Green here, the green curve is like using adaptive addition of operators. And blue is actually using the full unitary coupled cluster, the full 640 operators. And because there's an additional benefit shown that if you use this adaptive addition of the operators, you actually have a better convergence than if one would use the full operator pool from the beginning. I mean, this is not something new we found. This is in agreement with what people have found for adaptive VQE already, that adding these operators adaptively can help with the optimization not getting stuck. Okay, but I think now roughly in time come to the conclusions. So I hope that I could convince you that this transcorrelated method, by partially transferring electronic correlations from the wave function to the Hamiltonian and capturing the cusp, can reduce the qubit requirements and the circuit depth, since we then have more accurate results with a very small basis set and these more compact right eigenvectors. And if we then combine this with efficient error mitigation techniques, this method essentially extends the applicability of current near-term quantum devices to more relevant quantum chemistry problems. This is just a visual recap of my talk. And I also want to thank my collaborators at the Max Planck Institute on the topic of transcorrelation, especially mostly Ali Alavi and Pablo Lopez Rios, as well as my colleagues at Chalmers on the error mitigation scheme, the group of Martin Ram, and also the team of Ivano Tavanelli at IBM. Previously, Igor was also at IBM, but now is at Pascal. My current group is now in the process of being started. And also I want to thank my funding agencies that allow me to do the research. And I want to thank you for your attention.
Thank you, Werner. Very nice presentation, Werner. He talked about how to reduce the quantum circuit for
Yes.
current and near-term quantum computer using the transcorrelated method and adaptive circuit ansatz. Werner, I see some questions in the Zoom chat. Let me read them. Okay, first, this is from Dr. Gunara. He'd like to have your presentation file if you are okay. Maybe you, yeah.
Yeah, that's fine. That's fine. I can send it
Yeah.
to you after the talk.
Okay. And then second, this is from Dr. Hastio. His interest is in applying quantum geometric tensor in condensed matter systems.
Hmm.
He heard from other works the evolution in imaginary time in quantum circuit uses ancilla qubits. He's not sure the detail. Is this similar with your method? And do you say that the minimization of energy means the system chooses the optimized geometry of the manifold?
So, I mean, I'm not fully sure about the background, but I know that like the analysis of the quantum geometric tensor, like especially nowadays in solid state theory, is gaining like interest because there have been like essentially some connections made between the quantum geometric tensor, where like its real part is like this Fisher information, the imaginary part is the Berry phase, that there are some connections also to topological aspects and like Hall resistivity and so on. So I'm not quite sure if that's maybe slightly different topics, but what the quantum geometric tensor here, and especially like its real part, Fisher information matrix, for this approach, if you use parameterized quantum circuits, it does not need ancilla qubits because essentially you can efficiently measure just this expectation value, like the derivative of your wave function with respect to parameter I and j. But I assume that's very much maybe the different, maybe we can talk or also write via email later on. I assume that the other, I mean, I guess this is very specific to this variational representation if you use a parameterized quantum circuit, that you don't need ancillas.
Okay. I believe you are also answering. Have you answered the second one? Do you say that the minimization of energy means
Sorry.
uh,
No, I forgot. So the minimization of energy, can you repeat that part again? I don't have the chat open. I don't find it.
uh, does the minimization of energy means the system chooses the optimized geometry of the manifold? So
So, I mean, you can do, I would not, I'm not sure if the optimal geometry of the manifold plays a role in here, because essentially so you can also minimize by just doing gradient descent. I mean, there can be problems, but you don't have to include the geometry information in the minimization. So since the metric essentially is like independent of the energy, I don't think this is related specifically here. I mean, there can be, I mean, in machine learning, I could imagine that it might be different, because in machine learning, you can make a direct relation with essentially the samples neural networks. Like you can represent your neural networks as probability distributions, and then similarly this natural gradient minimization is also a thing in the machine learning community, where there it's, I think, a much more direct relation, because there you directly can minimize, for example, this how's it called, the Kubler this
Loss function?
yeah, you can define the loss function as this Kubler-Leibniz divergence. I forgot the name. So then you have a direct relation also with the metric, which here is not so direct.
Okay, so next, let's move to the next question. This is from Dr. Sudrajat. Uh, he thank you for your excellent talk, Werner. He's working on nitrogen fixation
Okay,
to
okay.
ammonia photocatalytically on solid materials. He's an experimentalist,
Mm.
not a specialist on first principle calculations. His question is, since light-driven processes involve excited states rather than the ground state,
Mm.
what computational approaches would you recommend as accurate for elucidating excited state energetics in such systems? Yeah.
So that's definitely an important extension. So there are like there are extensions of this VarQITE also to extend it to excited states. So that's also something me and my group will work on in the future. Um, and I mean, both classic, like both conventional, there are many conventional methods that can target excited state, but if we focus about quantum algorithms, so I think one of the most promising near-term algorithms that then will also allow the targeting excited states are twofold. I mean, they are both this so-called quantum subspace expansion methods. Like there's this quantum sample-based diagonalization that the IBM team has introduced recently, where there's a quite natural, easy extension to target also excited states. As well as quantum Krylov methods, where you create your Krylov subspace on quantum hardware, where also this can be extended to excited states quite directly, and they also have some benefits noise mitigation wise. So I would say these two methods in the near term seem to have the most potential. I mean, there are also this quantum computing, quantum Monte Carlo methods, where one uses then, for example, auxiliary field quantum Monte Carlo combined with quantum computing approaches, which also can make use of like the power of this conventional method or AFQMC to then target excited states.
Werner, can you repeat again the two methods for excited states?
So I would say it is
Quantum Krylov.
quantum subspace diagonalization.
Okay.
But these are very also sometimes called quantum selected CI methods,
Mm-hmm.
where essentially you create your Hamiltonian, you
Right.
create by samples taken from the quantum circuit. And then, I mean, if you have your Hamiltonian classically, you can very easily also extend it to excited states. And the other one was the quantum Krylov.
Krylov. Okay.
Yeah.
Thanks. His next question, what corrections are typically required when calculating Gibbs free energy?
Oof.
Well,
I should
uh,
know, but I cannot. I must say, I would need to read into that too.
do you want to skip?
I mean, I'm usually my methods I work with is
Just ground set or
t equals
excited?
0, ground
Okay.
state
Okay.
at t equals 0. I
Mm.
mean, I totally understand. I mean, if especially experimentally, you
Right.
definitely need to go there,
Mm-hmm.
but it's it's a difficult step because already the ground state t equals 0 solution is the bottleneck nowadays, I would say. So for these strongly correlated exponentially scaling problems. So I would say step by step, essentially, at least my work focuses on this. And then later on, I mean, of course,
Sure.
one needs that, but it's a bit out of reach, I would say, currently.
Next question. This is from Yoga. He's an excellent student. Instead of working using state vector in Hilbert space, is it possible that the transcorrelated method be adapted to work with shadow state that leverage Lie theoretical frameworks for efficient Hamiltonian simulation? So combining transcorrelated method with shadow state.
It's shadow state in the sense of shadow tomography, classical shadows, or I don't fully.
Yoga, you want to speak up, Yoga? It's okay. I'm not sure either, Werner. So
So I cannot answer then, I think,
okay,
because I mean, yeah, you can combine it also like with, so I think doing shadow tomography, classical shadows, is also quite naturally possible. With that, with the Lie theoretic framework, I would need to, yeah, get some clarification on the question to answer it, I think.
okay. Dr. Gunara asked, how about the degenerate cases? I think he meant for excited states. The two methods, the quantum subspace and quantum Krylov, could this also work? I think it works, right, Werner?
So, I mean,
Comment?
degenerate cases are usually difficult. I mean, it can add just like very just problems in numerics and theoretically. Uh, but yes, theoretically, like both these quantum subspace methods should also be able to target to deal with degenerate cases. With some caveats always, because I mean, usually if you have a degeneracy, like just doing the simulation is just very much difficult because you have inherently a more strongly correlated multi-reference character that you then need to take into account or deal with. So it's theoretically possible, but it always causes problems, except, for example, if you can uh, separate your degenerate cases based on symmetry, because often like degenerate cases solutions have different quantum numbers in some sense, like maybe a different total spin. And then if you can, for example, design your method to conserve quantum numbers, you can essentially avoid the negative impact of degeneracies in energy if you can treat them on this level.
Okay. While we are waiting for more questions, I have questions, Werner.
Yes.
Uh, I found that the TC method is evaluating three body integrals, right? Is it expensive?
Yes, that's a good catch. So in the preparation, like of preparing this TC Hamiltonian, you have to calculate these three body terms. I mean, as I mentioned, that you can have accurate approximations to them afterwards, but these are done in hindsight because you still need to prepare this Hamiltonian on conventional hardware. But it's expensive, but I think we have now like a very efficient Fortran-based library that evaluates these integrals. And I would say for the system sizes we can tackle anyway on quantum circuits, it's not yet a problem. If in the long run, it could definitely be a bottleneck if we can go to larger number of orbitals, qubits, then this become a bottleneck, this n to the sixth scaling.
Okay, maybe last question from me, Werner. Your transform Hamiltonian becomes non-Hermitian, right? I
Yes.
think that's a very serious. Can you comment the consequences of non-Hermitian Hamiltonian?
Yes, so as mentioned, I mean, the variational principle does not apply anymore. So one needs to adapt your algorithm to deal with that case.
Mm.
But essentially for targeting the energy, that's usually not a big problem. So there are many methods, like we combined it not only with quantum algorithms, but also with conventional quantum Monte Carlo with coupled cluster with DMRG, selected CI. So all sorts of algorithms have been adapted to deal with that. One drawback, the major drawback, I think, would be that since this non-Hermitian operator has different right and left eigenvectors, actually calculating other properties, like usually for other properties, you would target, for example, the one and two body reduced density matrices, and actually getting those is not so easy anymore. Because then you would need to have access to both the right and the left, and all the benefit you gain from the right being more compact, you actually pay with the left eigenvector becoming more complicated. Like so, there's no free lunch in that sense. So you just shift the cost a bit. So energy is good. Properties still an open question.
So the left eigenvector, we simply ignore it,
For
Werner?
the energy you can,
Ah,
because there are these projective techniques that essentially like quantum imaginary time evolution that just project onto the right eigenvector. So there you can efficiently, with no drawback, ignore the left eigenvector. But if you want to have properties, you need the left, and then this is still open research field of my group and also others.
okay. There is question, Werner.
Yes.
Uh, this is from ERA. Uh, Transcorrelated quantum imaginary time evolution addresses the cusp problem with higher accuracy and lower circuit depth. Yeah, that's the advantage of the method. Can we still maintain its convergence and obtain good dissociation profiles at large bond lengths with this approach? And what is the limitation of this approach? This is related to, is it dynamic or correlation, right?
That's maybe an important point to make. Dynamic correlation is often associated with essentially the need that you need this, that the cusp problem is equivalent essentially to the dynamic correlation problem. Like needing this very large basis sets is addressing the dynamic correlation of treating this sharp cusp-like feature. So transcorrelation naturally takes into account dynamic correlation.
Right.
Maybe one point, so the good thing also, and also maybe the convergence problem was meant in a sense that, okay, you have no variational principle. Are you sure that you converge to the right result? So yes, for methods like quantum imaginary time evolution, you can prove that also with this non-Hermitian, you converge to the right result. And also dissociation and like bond lengths are usually not a problem, I would say. I mean, there are always like more problematic regions of the bond dissociation region than others, but per se, this is not a limitation. I mean, it can be actually at large bond distances, it performs very well. Like at this intermediate bond distance, it can be with very other, like similar to other approaches, can struggle. Yeah, so I would say this is not an issue. I mean, it's on the classical part, how you optimize these Jastrow factors, that can be an issue because if you have then overlapping Jastrow factors between different atoms, you can have some double counting problems, but one can efficiently take care of that. One drawback I would say is, since you have this non-Hermitian problem, what you can have is if you then project like your TC Hamiltonian from first quantized into a basis set and second quantization, you can actually get results lower than the CBS limit, like the first quantized limit result. So usually, like
So
if you increase the number of basis set, basis set size, you converge
below the energy,
monotonically.
below
Come
the
again?
energy, below the
Genau,
average
yeah, for
energy.
this TC, you can actually converge from below. So doing then extrapolations to the CBS limit is not so easy. So this is a drawback.
Okay. Uh, it seems no more questions on the Zoom chat. So let's let's close our colloquium today. Thanks a lot, Werner, for your great
Thanks a lot for
presentation.
having me. Thanks a lot for
Yeah,
having
it's
me.
wonderful method, the transcorrelated. We saw the results, very promising and very accurate also. And thanks to all participants. We look forward to seeing you again at our next colloquium. Bye bye,
See you.
everybody.
Bye bye.
Bye bye, everyone.